So we have structural isomers. Structural isomers are going to have the same basic, like empirical or molecular form. Well, it depends on the molecular, how it's written. But they'll have the same elemental composition. But how things are arranged are structurally different. And so let's look at some structural isomer examples here. Like these two top ones here. This one is going to have 5 amines and 1 sulfato ligand attached to the chromium. And that's going to form the complex cation, and we have the chloride as a counteranion. Over here, this is the same makeup, in fact, all the same species, except the chloride's not a counterion here. The chloride is actually a ligand attached, and the sulfate's a counterion. So this is going to have 5 amines, 1 chloro on the chromium, and then sulfate is outside the coordination sphere. So the same formula, kind of, at least same compositional makeup, but different structure. So this is structural isomer. Okay. Here is another example of structural isomers. Here we have 6 amines, 6 cyanos, but it depends on what they're bonded to. These 6 amines are bonded to cobalt. So this would be hexamine cobalt 3, and this would be hexacyano or cyanido chromate 3. Over here, the amines are going to be bonded to chromium instead of the cyanos. So this is going to be hexamine chromium 3, and this would be hexacyanido or hexacyano cobaltate 3. And so it's just bonding the ligands to different metals in this case. But essentially all the same elements. And in fact, even the amines and the cyanos are the same. It's just structurally they're bonded differently. Okay, is this good? Okay, there's some more here. This is pretty much the same. We have, this is a typo here. This is a typo. But on one of these, we have the nitrite ion bonded with the nitrogen. The only difference is this one's going to be the oxygen bonded. And so we call this N, nitrito N, and this would be nitrito O. This is supposed to both be pentamine, so this should have been a 5 here. And then there's another inconsistency. Do we put the anions first or the neutrals first? And so, I'm not going to be such a stickler for the rules. And so essentially it's the same. It's, depending on what is bonded, the nitrogen or the oxygen. Same, overall formula. And this is different than stereoisomers. The first stereoisomer we'll look at are the geometric isomers. For the geometric isomers, we have cis and then trans. The cis, the 2 greens are adjacent to one another. The trans, they're opposite. This would be cis here. This would be trans here. Now, when you have 3 of a kind in an octahedral structure, those 3 can be on the face of the octahedron, or they can be along the edge of the octahedron. If they're along the edge, we call it the meridional or the mer isomer. If they're on the face of an octahedron, we call it the facial isomer and face. Perfect. And so all the bonds are the same. I mean, if we look at platinum here, it has 2 chloros and 2 amines. Look at this one, 2 chloros and 2 amines. Structurally, they're the same. What's different between these two is how they're arranged in 3-dimensional space. And so they could be adjacent or opposite. but they all have the same bonds. In fact, when we look at the formula, we can't tell the difference looking at the formula. Up here, we can tell the difference looking at the formula because the formulas were different for the different structures. Down here for geometric isomers, we can't tell. Since we can't tell, then we add the little prefix here. For example, cis. That tells us that the two chloros are adjacent and the two amines are adjacent. And then we have trans, which are opposite. Now, these are going to have different properties, the cis and the trans. They're going to have different boiling points and other properties just based on the small structural difference. It's not so small, actually. This one's a very famous one. Did I mention this? The common name for this one? This one's called cisplatin. And it's very famous because it's a powerful anti-cancer drug, this one. And the history of how it was discovered is very interesting. The people who discovered cisplatin at the University of Michigan, they are testing how electric and magnetic fields impact the growth of tumor cells. And so what they did was they took a couple of platinum electrodes and then stuck them in a culture of cancer cells and then turned up the voltage. When they turn up the voltage, it creates an electric field, like one end turns positive, the other end turns negative. And they wanted to see, if there's an electric field or magnetic field or both, electric and magnetic field present, how does that influence or does it have any effect on cancer growth? And do you know what happened? What do you think? Does it have an effect on cancer growth? You would think so, but they never got that far, I think, because you know what happened? What happened was the platinum electrode started reacting with the cancer cell medium. And that's very unusual. Why is that so unusual? The platinum electrodes started reacting. Normally, we don't want the electrodes to react. And so it's unusual because platinum has such a high or such a low, what do we call it? Platinum is very unreactive because it has such a high or it has such a low. What? Well, metals are subject to oxidation or reduction. So it has such a high oxidation or such a low oxidation potential? Well, high oxidation potential means what? It's highly susceptible or it's highly unreactive? High means unreactive or high means reactive? High means reactive. So platinum has such a small oxidation potential, such a low oxidation potential that it's very unreactive. And that's why they chose platinum. They didn't want the platinum to react. All they wanted was the platinum was the inert electrode and they wanted to generate an electric field. But since the platinum started reacting, then that was unusual. Whatever was in that medium was able to get the platinum to react. And not only that, the product of the reaction killed all the cells. And so it's very effective at killing the cancer cells. And so they generated a tiny amount of this platinum compound, and this platinum compound turned out to be quite toxic for cancerous cells. And so what they wanted to do is they wanted to find out what the platinum compound was or is, what is it? And that's not so easy to do because that means you have to separate out minute quantities. They didn't have such a high yield of this stuff. If they had a huge yield and they were collecting grams of it, it'd be easy to isolate, purify, and then characterize. Well, characterization may not be so easy, because if you're characterizing it like us, looking at the crystals and the color, then it's not so easy. But if you're characterizing it and you have some equipment like melting point and X-ray diffractometer and other things, then it might be a little bit easier to characterize it. And so they didn't isolate, purify, and characterize this. You know what they did? They went and looked in chemical catalogs, and they bought every single platinum compound they could buy, and they tested those, one by one, and then they finally found one that was quite potent at killing cancer cells, and it was this. And so this is how they discovered cisplatin. They just bought a bunch of platinum compounds off the shelf and did this trial and error. But anyway, it's still used today. Transplatinum doesn't work at all. Transplatinum. Sometimes it's hard to make. Sometimes you only make one of these. Sometimes you make both of these. It's just all probability. And it depends on what atoms break and form. Oftentimes you make a mixture of these, cis and trans. All right, so these are geometric isomers, and the geometric isomers again are cis, trans, mer, base. We also have optical isomers. Everything looks the same, except one of these is just bonded slightly differently. I mean, if you look at this one, we have a cobalt-3 here, and there's 3 ethylene diamine. And this looks like the same thing here, cobalt-3 with 3 ethylene diamine. But it just turns out that the way they're attached are slightly different. It's like this blue marking here. These look the same, except they aren't the same. These are mirror images, and what we say is these are non-superimposable mirror images because no matter how you rotate this box, you cannot get these two blues to coincide. So if you rotate it 180 along the z-axis, then the blue ends up on the wrong side. Not on the far side, but the near side here. And so some molecules do the same kind of thing. It depends on how the ethylene diamines are attached. So if we look at these, okay, this is attached like this, but then the top goes to this rear here, the top goes to this rear here. But if you were to rotate this 180, then the top goes to the front one. The top goes to the front one, and the bottom one goes to the back one. And so they don't match. And so if I rotate, it's like the left hand and right hand. If you rotate one of the hands to try to match it, it doesn't match. The thumbs aren't in the same position. And so the same thing happens with these molecules. We call these optically active. The origin of optical activity is one of these rotates light one direction because the light interacts with the electrons and the bonds. And the bonds are in a different position than in the other one. And the other optical isomer rotates light in the opposite direction. Normally when we make these, you make what's called a racemic mixture. A racemic mixture is a 50-50 mix. That is, half of it's this, half of it's that. And so we end up with this 50-50 mix. Now, when we have this 50-50 mix, what happens is one rotates light one way, the other rotates it the opposite way, and then it becomes optically inactive. So 50-50 racemic mixture of this is optically inactive. What we need is we just need the pure form. Now this is, this doesn't seem to impact things too much. The properties are going to be very similar. The crystals may look a little bit different, but overall they should be very similar in properties, in fact the same. Unless it's a biological system. When you're working with biological enzymes, which is a biological catalyst, then it's very sensitive to position here in three-dimensional space. So one of these will be biologically active, the other one won't. It's like ibuprofen. Ibuprofen, if you take a tablet of ibuprofen, half of it's wasted, half of the active ingredient's wasted. So let's say you make a ton of ibuprofen, half a ton is waste. Half a ton is waste because it's the wrong structure. Because your enzyme can only digest, let's say you have an enzyme like this, so it can only digest the ones that fit here. It can't digest the right hand, but you form both of them. Because it's just statistics, probability. And so this is important in biological systems. So how we can tell if something's optically active? There are two ways to tell. One, draw its mirror image. So here, I draw its mirror image, and then see if I can rotate this to superimpose it. When I try to rotate this one, if I rotate this one, I can line up this ethylene diamine with this ethylene diamine. But when I look at the back, the top goes to this corner and the bottom goes to that corner, so they don't match. They're mismatched. And then if I try to rotate it 180 the other way, it still doesn't match. So no matter how I rotate this, I can't get it to match this. And so this is a unique structure. You don't always have to draw the mirror image. We can tell if something's optically active if it doesn't have a mirror plane. What a mirror plane is it's a plane where you can slice the molecule in half. So if we slice the molecule in half right here, we'll get two equal halves. That's called a mirror plane. And if we get two equal halves, then it's optically inactive. So this molecule I can slice in half here. This would be optically inactive. This molecule I can slice here and get two equal halves. That would be optically inactive. This molecule here I could slice in between the two greens this way and slice right through the middle of the blue atoms here. This would be optically inactive. This one I'd just slice it down the green, 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 and these two blue here along this plane. It's a mirror plane. This one I just go right between the two greens here, slice it there. This one I just slice down the middle here along the plane. So none of these are optically active. Sometimes it could be. So for example, the one we did in lab was the cis dioxylato. That was the cis, it had the two chloros, the two greens. That was optically active.
How do you know where to slice them? Because I mean, depending on where you slice them, you could have two halves of anything.
Yeah. So can we slice this box in half and get two equal halves? Well, the blue is only here. So is there a way to slice this box in half and get two equal halves, identical mirror images of each other halves? And it turns out that there's no blue around the corner, because if that were the case, if this blue expanded around the corner, I'd just slice it here.
Yeah.
And then I get two equal halves. But if I slice it here, then I only get blue on the right half, and on the left half, I have no blue. Then I think, okay, how can I get half the blue on one side and half the blue on the other side? And there's no way to do it. Unless the blue extended all the way to the top and there's a lid, then I'd be able to slice it in half right down the middle here, get two equal halves. But do you see they stopped the blue here at the midway point, so you can't slice it in half. And so this would be it. But whereas this, you could slice it in so many different ways and get two equal halves. And so this would be optically inactive. This would be optically active. And when it's optically active, we call these enantiomers. These are two enantiomers of this box. These are two enantiomers in this structure. There's no cis-trans isomerism here. There's no mirror face isomerism here. There's no geometric. There's just optical isomers here. And so when we look at structures, we first look, for geometric isomers, and then we could look for optical isomers. So the trans isomer of this is optically inactive, but the cis isomer of that is optically active. And so this is one we built, or similar to one we built. And we had oxalato ligands. This will be ethylene diamine ligand. And so if we do, let's say, this is chromium. Let's do the trans isomer. So I'm going to put the two chloros up here. One chloro up here and one chloro down here. And then I'll do ethylene diamine. Ethylene diamine I'm going to draw like this. Can you slice this in half and get two equal halves? Yeah. We can slice it in half right here and get two equal halves, or slice it in half here and get two equal halves. That's one way. The second way is if you can't tell there, you draw its mirror image. So when we draw the mirror image here, and look, they're identical. Right? We don't even have to rotate it. We can see the same thing. If they're identical, then forget it. It's not an isomer. An isomer should have a different structure. Now, if we do the trans isomer, this is the trans. If we do the cis isomer, okay, so let's do the cis isomer here. Put a chloro there, chloro here. And then maybe we'll do an ethylene diamine here. And an ethylene diamine here. Okay, can you slice this one in half some way and get two equal halves? Is it possible? No. And not only that, if we do the mirror image of this, and then rotate it. So I'm going to rotate it to make sure these two match. Actually, oops, I didn't do this. Is not the mirror image. I drew the same structure. Into the mirror image. So this one's going down and it's coming to this one coming out. Good. Oops. Missing one chloride. All right, now I think I finally got it. So what I'll try to do is I'll try to match maybe this one and this one. So I'll rotate this 180. But when I rotate it 180, then this chloro is going to end up sticking out here, not the nitrogen. So I have a chloro sticking out, and then that nitrogen that's linked to the bottom will be sticking in here. And so if I were to rotate this 180, you draw this here, I would, I'd have this line up. That's good. I have the chloro line up here. But what I'm going to get is I'm going to get a chloro coming out here, and then nitrogen from the ethylene diamine coming out in here. So then I see that they don't match. And then I see, well, maybe I'll flip it this way. But if I flip it this way, then the chloro is not going to match over there. And so these are two enantiomers, or these two. Those are two enantiomers. These two are the same structure here. So we have two isomers. And so in this compound, we have a total of three isomers. We have the trans isomer and two variations of the cis that are mirror images of one another, non-superimposable mirror images of one another. So we're going to look at another thing about complexes. Complexes, what's going on with electrons here? What's going on with electrons are these bonds are coordinate covalent or dative bonds. So both bonding electrons come from the donor, the ligand. What's going on with the electrons in chromium? Well, chromium is going to have some d electrons, and those d electrons are in the d orbital, and those d orbitals don't participate in bonding. Those d orbitals are called non-bonding orbitals. And they're just sitting there, so there could be electrons sitting in d orbitals. And so this is showing an octahedral complex with ligands coming in. Well, the ligands are going to be electron pair donors. Now, if they're just electrons sitting in these d orbitals, not participating in the bonding, then we're going to get electron-electron repulsions occur. And so the electrons on the ligands are coming in and then causing repulsions with the electrons in the orbitals. And so what happens here is this. We'll have 5d orbitals, and they're given by these different shapes here. And when we bring an octahedral field, we call this a field of ligands, then all those d orbitals are going to go up in energy because of the electron-electron repulsion. But they don't all go up in energy the same amount. Some of these go up more. So for example, the dx squared minus y squared, the ligands come straight into the lobes along the xy plane. In the dz squared, the ligands come straight into this hula hoop here. And that causes these to go up in energy more than these. When I look at the dxy and the others, the ligands come in between the lobes, not directly into the lobes. It's hard to see. They're coming in between the lobes. And so that's going to lead to uneven interactions between the ligands and the d orbitals. And we call this crystal field splitting here. So this is the characteristic pattern for octahedral. One of the things that we note is the splitting pattern. This is a 2-3 splitting pattern. You don't have to have this memorized. And then we have something called delta. Delta is the degree of splitting. Depends on how much the ligands interact. If the ligands strongly interact, then the splitting is large. And so for large delta, we have things like cyanide, nitrite, ethylene diamine, the carbon and the nitrogen donors, followed by the oxygen donors and the halides. The halides don't really interact as much, so the splitting is going to be smaller. So there's a smaller gap here. Now, if we have electrons here, what that's going to have an impact on is color and magnetic properties. Because usually the splitting is about a UV photon's worth, or maybe not UV, visible photons worth. UV would be colorless. If this absorbs visible photons, that is, electron down here gets promoted to up here by absorption of visible photon, then it's going to be here colored. And so what happens is things like ruby will have a little bit of transition metal. Normally ruby is totally colorless, but there's some transition metal, and that transition metal is surrounded by a field of ligands, and that causes a splitting, which causes the ruby red color, absorption of light. This is octahedral. The splitting pattern for tetrahedral is different. In this tetrahedral, we have a 2-3, 3 up high, 2 down low, and that depends on how the ligands interact with individual orbitals. And so that interacts with these 3 orbitals more than it does these 2 here. And that gives us splitting here again. The d orbitals aren't all equal. But for tetrahedral, it's pretty weak. And so the delta is only about 4/10 that of the octahedral. So it's a much weaker interaction. For square planar is like octahedral, but you pull off the Z ligands. If we do that, then we get something like this, where it's like a 2-1-1-1 splitting pattern. Delta is fairly big for square planar. This delta here is smaller, but the overall delta is pretty big. All right, so this is going to lead to different colors, depending on what ligand you have attached. How it leads to different colors is due to the crystal field splitting energy. So you could have the same metal cation, but with cyanide. With cyanide, you get a big delta. If you have a big delta here, that means you need a high energy photon. A high energy photon comes here and promotes it. Well, a high energy visible photon would be like violet, indigo, blue, green. Those would be higher energy photons. And a higher energy photon, if I have an electron down here and I want to promote it up here, is going to be required. So if something absorbs red, that would be a low energy photon versus violet, which would be a high energy photon. it gives quite a bit different color, even though we might have the same central metal. And so if we look at copper with cyanide versus copper with chloride versus copper with water, we'd expect different colors. And the different colors is because of this. Cyanide is what we call a strong field ligand. Cyanide is a strong field ligand, which is going to lead to large splits here. A large split means higher energy photons like indigo, violet, blue, green. Photons have to be absorbed as well. Whereas chloride is considered a weak field ligand. A weak field ligand is going to have a smaller split here. And so if the splitting goes down here, then we absorb lower energy photons like red, orange, yellow. And so what color it appears depends on what we absorb. And so here we're going to have red, orange, yellow, green, blue, indigo, violet. So cyanoligand is going to absorb high energy and appear as low energy. And so what that means is this, like a cyano complex might absorb around here, indigo, violet, blue, and when it does, it appears these colors, orange or yellow, a lower energy color. Whereas the chloroligand is going to absorb low energy, but appear high energy, a high energy color. So if this absorbs low energy and appears high energy, then kind of the opposite scenario happens. We'll have red, orange, yellow, green, blue, indigo, violet. And let's say we absorb red, orange. If we absorb red, orange, then the color it's going to appear will be higher in energy, like blue, green. Or if we absorb yellow, it will appear indigo, violet. So green light is higher in energy than orange, yellow light. And so that's the scenario. The color is going to depend on what ligand you have in there, because it's going to change how much energy is required to absorb to promote that. So here we can see, chloro versus aqua ligand. The aqua ligand up here absorbs in the yellow region, and so it appears blue. So aqueous copper is a light blue color. Whereas if you have lots of chloride in there, then it absorbs in the blue region and appears yellow. And so a solution of the aqua complex is blue, the solution of the chloro complex is yellow. It's still copper, too. In addition to color, we also look at magnetic properties. So here are two complexes of cobalt. Both of these have cobalt in the +3 oxidation state. Let's use this periodic table here. So here I've got cobalt, and cobalt's electron configuration is argon, 4s2, 3d1, 2, 3, 4, 5, 6, 7. 4s2, 3d7. Now, if I go to cobalt +2, which electrons get ionized? The 4s electrons or the 3d electrons? So I go cobalt +1, cobalt +2. Which electrons get ionized? You would think the 3d, but it's the 4s. The 4s electrons get ionized. And so if I look at cobalt, this is +3. That's actually, let's go to cobalt first. Cobalt neutral. Cobalt neutral has an electron configuration argon forest 2, 3d7. Cobalt 3 plus is just going to be argon, and the forest electrons we're going to lose. So it's going to be forest 0. And then it's going to be +1, +2. And what number are we at? We're at number 7. And so this is D7. It's called D7. So it's argon 3d7. So we have 7 d electrons. We'll put those in the orbitals. These are non-bonding. They're just hanging out, but they're being interfered with by the ligands. And the ligands are causing a splitting here. This is octahedral, 3 down, 2 high. Okay, so we put in the 7 here. Now this gap isn't so big, even though this is visible light, let's say, this gap is pretty small. So what we have to worry about, and this is something we don't normally have to worry about because usually kind of the gap is kind of big, at least down low. No, sorry. Cobalt 3 plus is +1, +2. I did only +2. +3 is not 5. +3 is 2 ways you could do it. I lose 2 of my s electrons and 1 of my d electrons. Sorry, this is 3d6. And so I lose 2 of the s and 1 of the d's. That gives me d6. The other way I could do it is by using the periodic table. This is the way people normally do it because it's fast. If you want to figure out how many d electrons you have in an ion, we do it like this. Cobalt +1 would be 8, +2 would be 7, +3 would be 6. Nickel +2. So we go +1, +2, 8, D8. Copper +2. Copper +1, D10. Copper +2, D9. Zinc +2 would be +1, +2, D10. That would be zinc. And so we could use the periodic table to do this, which we'll do later. But there's 6 d electrons. Normally we follow the off-bound principle. The off-bound principle says fill the lowest energy orbitals first. But when we can deal with complexes and the splitting, this splitting isn't so big. So we have to worry about pairing energy. When you put 2 electrons in a single orbital, there's negative charge repulsion. And to minimize that, we put them in separate orbitals. So it depends on how big this gap is. This gap is called delta. Delta O stands for octahedral, so this would be the octahedral crystal field splitting energy. But the delta is small in this case. So if delta is small, then the pairing energy could be greater than the promoting energy. And so when we fill this, we fill it 1, 2, 3. Do we pair or promote? We promote. So it goes 1, 2, 3, 4. Why? Because promoting costs less energy than pairing. And so 1, 2, 3, 4, 5. And then finally we have to pair. We'd rather pair lower energy than a higher energy orbital. And so this gives us 6. That's with fluoro ligand. Fluoro doesn't split this much. But if we go to amine's a much better ligand, it's going to split it more. And so here the promoting energy is greater than the pairing energy. So when we do this, it goes 1, 2, 3, 4, 5, 6. All the electrons are paired. This gives it drastically different magnetic properties. So hexafluorocobaltate 3 is paramagnetic. It has 4 unpaired electrons. Whereas hexamine cobalt 3 is dimagnetic. All the electrons are paired. And dimagnetic compounds are repelled by magnetic fields, Jen. But paramagnetic are strongly attracted to magnetic fields. So we'll do paramagnetic material here. And so we can understand, the d orbitals are going to interact with the ligand, and And what we end up with is crystal field splitting. Crystal field is the crystal field of ligands split. We can split it into octahedral, tetrahedral, or square planar, which all have different splitting patterns and different magnitudes of delta. Tetrahedral deltas are always small. And so this is what we call, when we promote, we call this high spin. High spin is promote. Low spin is paired. So it depends on what ligands. If we have strong ligands like these, those are going to be low spin. This is hard to promote. If we have weak ligands like these, then these are going to be high spin. We'll rather promote versus pairing. Over here, the tetrahedral, the interaction isn't nearly as strong, so all tetrahedral complexes are high spin. You don't have to know that. But the ligand interactions aren't as strong. In square planar are low spin. That is, you fill the lower energy ones before going up. These are high spin, meaning you fill the low and then jump up. You promote before pairing. All right, so that's chapter 24. We'll take a break and then we'll just go through a quick survey of chapter 25. I don't have that many slides on chapter 25. So let's take a break and we'll start up again.